Hi, it's Dr. Archie here, and I just want to work through a few examples to show you how you can use the fundamental theorem of calculus to avoid having to do the rectangles thing. Okay, so first thing we're asked to do is use the fundamental theorem of calculus to compute these two integrals. The one on the left is an indefinite integral, and on the right we have our definite integral. We'll start on the left. That's why I set them up that way. Okay, so I'm asked to find the antiderivative of 5x cubed. And here's a way you might think about that. You might say to yourself, well, let's see. Thinking about the power rule, if I had maybe x to the fourth, then when I took the derivative, I would get 4x cubed. So that's not quite right because I have a 5 here instead of a 4. So if I kept the 5 and put something that would cancel out the 4, then when I took the derivative, I would have 5/4 times 4 x cubed. And the 4's would cancel. Perfect. So then I'll write down my answer now that I've figured out what it's going to be. It's 5/4 x to the 4th plus a constant, because it's always plus a constant. And let me put this in sort of a thought bubble over here. All right. Now, if instead they had asked for this definite integral from -1 to 1, then the first thing we would do is this process to try and figure out what the equation should be. And then we'd write down, okay, it's 5/4 x to the 4th. But now I don't need to write the constant, it would cancel out anyway. And I'm going to evaluate from -1 to 1. So what I do, I'm like, all right, 5/4, plug in the 1, raised to the 4th power, minus 5/4, -1, raised to the 4th power. Okay, and then I do some arithmetic. 1 to the 4th power is 1, so I'll just have 5/4 over here. On the right, I have -1 to the 4th. Wait, that actually also is 1. So now I have minus 5/4 for a grand total of 0. Let's try the next one. So in this second example, just like in the first one, I start out with being asked to do both the indefinite integral and the definite integral of the same function. So I'll look at this indefinite integral and say, okay, what should I do about this? And you might be thinking, wait, I don't really remember any derivatives that come out looking like that. But maybe you remember this technique from taking derivatives in which we found it really useful to rewrite things as powers instead of roots or instead of 1 over things. So you might write this instead as x to the minus 1/3 dx. And now it is something that we can do antiderivatives of, because think about this. All right, if I increase the power on x by 1, I would get up to 2/3. So minus 1/3 plus 1. 1 is 3/3, right? So that's 2/3. So that's good. Okay. Now, is this the antiderivative? Well, I take the derivative to double check, and I would get, okay, decrease the power by 1 and bring down the original power. So that isn't quite what we started out with up here, right? I picked up an extra 2/3. So I'm going to fix it by putting in an extra 3/2, because then I will get the right thing. So what's my antiderivative? It's 3/2 3/2 times x to the 2/3 plus a constant. So that's the answer over here. Now for the definite integral, what I would do if I hadn't already done the indefinite integral is I would start out thinking through this same procedure, and then I would say, okay, so first I write down the formula, 3/2 x to the 2/3 of the antiderivative, and then I'm going to evaluate from -8 to 1. So that's 3/2 times, first plug in 1 to the 2/3 power minus -8 to the 2/3 power, close parentheses. All right, so what's that? It's 3/2 times, okay, take 1, cube root it, I get 1, square it, now that's still 1. All right. Okay, take -8. When I take its cube root, I get -2, and then I square that and I get 4. And so that's 3/2 times -3, or if you prefer, that's -9 over 2. All right, last example. Now this one looks a little bit like the last problem, and you might be tempted to rewrite this in some different ways. Like, okay, first of all, I want to think about the 1/2 as like a separate thing. That's just a constant. So if I think about 1 over x dx, you might think that it would be helpful to rewrite this as 1/2 times the integral of x to the -1 dx. But -1 is a special case because if you add 1 to that, you get x to the 0 when you just have a constant, and it's not really quite where we wanted to go. And besides which, you never get 1 over x by taking the derivative of x to a certain power. In fact, you only get that derivative, so that was not helpful, true, but not helpful, of the natural log. And it turns out you need absolute values there, plus a constant. Okay, right. So once again, if it was a definite integral, what would I do? First thing I would do is think through an antiderivative, then come back and plug in. All right, so what have I got? Let's see, 1/2 times natural log, the absolute value of x. Okay, evaluate from 1 to e. So that's 1/2 times natural log of e is positive, so I'll just put e, minus natural log of 1 is also positive, just put 1. All right, now the natural log of 1 is 0. And since natural log is log base e, natural log of e, that's 1. So that actually it's 1 minus 0 in there. So my answer is 1/2.